covalent bond, obviously these are attraction of nucleus, both the nucleus and both the electrons. Okay, so they are attracting each other. Now, if you have more electrons shared, there's going to be more attraction. There's two electrons shared, there's going to be less attraction. If there's one electron pair shared, that is even less attraction. But this is called single bond, this is double bond, and this triple bond. And single bond is going to be weaker. Double bond is usually, if we are talking about the same atoms, then double bond will be stronger and triple will be even stronger. Okay, so that is how covalent bonding comes into effect. We show this as a dot and cross diagram. For example, over here, I have not drawn these circles around them, but chlorine, for example, it is in group 7. It has 7 electrons in the last shell. So what does it do? It shares one with the other chlorine, and that way it is able to make this thing. So this is a dot and cross diagram, and this is called a Lewis structure. Okay, so you should be able to draw both of them. Similarly, over here, water Water has this structure that oxygen shares one electron with one hydrogen and one electron with other hydrogen. And that way, oxygen is able to make two bonds, one with hydrogen, one with other hydrogen. Similarly, nitrogen, which needs three electrons, it can form three bonds. So it can either form three bonds with itself or it can form three bonds with other things. For example, in this case, ammonia, nitrogen is sharing one with this, one with this, one with this. And this is ammonia molecule. Okay, so this is a dot and cross diagram for this. There are a few molecules in your syllabus for which you need to know how to draw this. For example, over here, carbon dioxide, we are seeing double bonds. Every carbon has 4 electrons, so it needs two more. So what has it done? Carbon shares 2 electrons with oxygen, and electrons, 2 electron pairs are shared between carbon and oxygen. Similarly, over here, 2 electron pairs are shared. So that is this thing. Similarly, over here, this compound, which is ethene, you don't need to know the name as yet. But what's happening here is that 2 electrons are shared between these carbon atoms, and one pair is between hydrogen and carbon, and one pair is between this hydrogen and carbon. And they're represented by different diagrams, different symbols, dot and cross. Here we have shown them as filled dots and unfilled dots to show that they are from one carbon or the other. But if you're doing it in the exam, you don't have to. You can simply use dot and cross as you seem fit. And this will be the Lewis diagram. You see, every time there is a line, we are putting a pair of electrons over there. Here we have triple bonds. So nitrogen is sharing 3 pairs with the other nitrogen. So that is shown as this. Similarly, this compound, which is C2H2, you do not need to remember how to draw this, but this has triple bond between carbon. This is called acetylene. And this is one of the things that you need to memorize, that acetylene is used for welding metals. But again, we'll get to that when the time comes. So you see, we have these different uh, substances. They are compounds, they're elements, and they have different types of bonds, single, double, triple. But overall, they're just sharing electrons. And whenever they share electrons, that is covalent bond. Okay. So here you can see that this is one molecule. This HCl is one molecule. What's happening? Hydrogen is sharing one electron with this chlorine and forming HCl. Similarly, oxygen is sharing 2 electrons with this oxygen and forming an oxygen molecule. When we write this, we will write this as H with a small 2 to show that there are 2 electrons there. Similarly, this will be HCl, which means there's one hydrogen and one chlorine in the molecule. This will be O2. So 2 will be small, and it will show that there are two atoms of oxygen combined together chemically to form oxygen molecule. And that is, of course, N2. Now, remember, N2 does not mean that it has double bond. It simply means that there are 2 atoms of nitrogen in the molecule. How are they bonded? You have to look at their group number to see how many electrons they need to share. Okay, so that's covalent bond. Over here, we have some covalent compounds. For example, this thing is called methane. What's happening is that carbon is sharing one hydrogen with this, one with this, one with this, and one with this. And that way you're able to do this. Now, how will you be able to draw this? To do that, what I would suggest is that you first start by drawing these circles. So this is carbon, this is another hydrogen, this is another hydrogen, this is another hydrogen, and this is another hydrogen. Okay. Then you place their symbols. So this is C. Here we have H, and we'll have H here, and we'll have H here, and we'll have H here. So this is to show that all these are hydrogen atoms, and that's carbon. Now, when you're filling these electrons, always start from the outside electron. So when you're drawing it, make sure that you first deal with hydrogens. Why? Because they're the outside ones. Once you fill it for hydrogen, then look at what the inside atom has. So remember, in all the compounds that you'll be asked to draw in the exam, there will be a central atom. And that central atom, in this case, is carbon. In the case of ammonia, it is nitrogen. In the case of uh, water, it is oxygen. So all the atoms, the other ones, they're going to be surrounding that central atom. So you simply draw circles for those, and then you connect them through crosses and dots. So here's what I'm going to do for you. I'm going to draw this structure for you. So over here, I'm going to start with hydrogen first. So this hydrogen gets a circle and a cross to show that there is one electron pair shared. This is again like this is again like this, and this is again like this. Now that I'm done, I need to look at, do I have any electrons left over for the hydrogens? I don't, because hydrogen just has one of its own. And for carbon, it has shared 4 already. So a common mistake the students do is that they think that, okay, carbon has to have 4 of its own, so they put those somewhere else. Remember that they are already taken care of in the bonding, in the bond pair that they have. Let me do it for water now. And I would like you to do for other things. So this is water. There's hydrogen on one side and there's another hydrogen on one side. Why am I drawing it like that? Because oxygen is the central atom and there's hydrogen on the sides. Okay. Now I'll start filling electrons from the outside atoms first. So hydrogen, one pair. This hydrogen, one pair. Hydrogen has one electron, it has shared that. Okay. Oxygen has 6 electrons. 2 have been shared. The remaining 4 must be drawn. Now, a good technique to do this is that whenever you put electrons, always put them in pairs when you're drawing these diagrams. Okay, that will help. So instead of scattering them around, put them in pairs. All right, so take a few minutes and try to draw a couple of these atoms or molecules. Yeah, so if I were to draw it for phosphorus trichloride, this thing, what will I do? I'll put phosphorus in the center, draw 3 chlorine on the side, and start filling electrons. Now to do that, I will have to see, okay, I'll start with the chlorine first, the outer electrons. So this needs, it's in group 7, needs one more electron, so it will share one pair. I'll use another color. Similarly, this in group 7 needs one pair. This also needs one pair. Now I know that chlorine has 7 electrons of its own. One it has shared, the other are going to be over here. And I can use either a cross or a dot, my choice. Same with the other chlorines. Same with the other chlorine. Okay. Now phosphorus is in group 5. I can see that it has shared 3 electrons. It will have 2 left over, which I will draw as dots or circles to show that they are different things. This is PCl3. How do we name these things? Whenever you name these things, you have to remember to name each of these elements. Okay. And the numbers here, these numbers have names for them. So for example, 3 means, 1 means mono, 2 means di, 3 means tri, 4 means tetra. Now the last element will have IDE at the end of the name. Just these 2 things that you need to remember. All right, so let's try to name this one. This is phosphorus, okay? And there are 3 chlorines there. So it will be tri and chlorine, chlorine. But because this is the last one, I'll say chloride. So phosphorus trichloride. Similarly, this thing is just an element, so we call it nitrogen. Okay, let's try to name this thing. I have carbon and I have two sulfur, so that is disulfur, but I have sulfur as the last one, so I'll say disulfide. Okay. Here I have multiple. So for the first one, I'll say dicarbon because I have two carbons. And then I have four hydrogen, so tetrahydride. Ide because it's the last one, tetra because it's four. And that's exactly what I'm getting. This is telling me there's two carbon and there's four hydrogen making it up. So C2H4. Some compounds have their names which are well known. For example, this one is called ammonia. Although we can name it to be nitrogen trihydride, but this is called ammonia. Similarly, this one is called hydrogen peroxide. So these are some things for which you need to remember the name. Similarly, this one, you don't need to remember this one. This is hydrazine, but you don't need to remember that. Similarly, SO3 here, its name will simply be sulfur with three oxygens, so trioxide. So you see, every time we have these compounds, we can simply name them based on the technique that we have. And it's pretty simple. We need to know how many atoms of those are there in the molecule. So one is mono, two is di, three is tri, and four is tetra. So these are some examples of these molecules being there. This one, for example, is sulfur atom. Sulfur over here, there are 8 atoms joined together to make this sulfur molecule. Each yellow one is supposed to be one sulfur atom. Similarly, this is phosphorus atom. What's happening? Every phosphorus is joined with other phosphorus and they're making this structure. And this means that every phosphorus is making 3 bonds. Why is it making 3 bonds? Because it's in group 5. It needs 3 electrons to share. This one is silicon. And this structure is pretty important because this is the same structure that we see in carbon. This is silicon attached to another silicon, attached to another silicon, attached to another one and another one. In total, every silicon atom is making 4 bonds. And why is that? Because it's in group 4. It needs 4 electrons to share, which is why it's getting these 4. All right, so let's see. We are saying that barium is making a covalent bond. Now, barium is in group 2. It usually does not make covalent bond. Okay. But because we're insisting that no, it is forming that with oxide ion. So this oxide ion is oxygen with 2 electrons shared in them. So that is this, the one that we see already. The answer over here is a little more complicated than that. And the reason is simple. Barium here, it is positive 2, group 2. So oxide, the peroxide ion must be negative 2. So first of all, let's create the oxide ion. That will be oxygen sharing 2 electrons between itself. Okay. And 2 of its own will be left over. All right. But this is oxygen molecule. How do we create it for this one? You just have to see that the total electrons are the same. And your answer over here will be D. So it's a quite challenging question. But the questions like these will not be on the exam, of course. They're much easier than this. Yeah, barium oxide is ionic, barium peroxide. But the peroxide ion itself is a molecule formed by covalent bonding. D is covalent because what D has done is 2 oxygen atoms are joined together by a single bond. You can see that. Okay. And it has gained 2 electrons. So you can have molecules joining and forming ionic bond. And why does that happen? Because non-metal anions can simply form bonds with metals. So example of those are abound. For example, nitrate, sulfate. You see, sulfate is iron. Nitrate is iron. Carbonate. These are all ions made of non-metals. Ammonium. What is the bonding inside these? So this is a question that they sometimes ask in the exam, that what is the which of these compounds has two types of bond. So you see, inside these, they have covalent bond because they are non-metals. But when they form bonds with other metals, that will be ionic. All right. So remember that whenever you see non-metals joining together, they will form covalent bond, sharing of electrons. But they can react with other metals through ionic bond. So metal plus non-metal, ionic, non-metal plus non-metal, covalent. All right. Similarly, we also have to sometimes count the electrons that are involved in bonding. For example, this is the structure of AS2SO4. Now, can you identify how many electrons are being shared in covalent bond here? How many electrons are being shared in covalent bond? So what's the right way to do this? You simply look at these lines, these pairs, and each line shows a pair. So you can see that there is one pair between hydrogen and oxygen, one between sulfur and oxygen, and two with the other sulfur and oxygen. So in total, there are 8 pairs. So that is 16 electrons shared. All right. Now, how many valence electrons are not shared? So that's a question. How many valence electrons are not shared? Okay, so because we want to know how many electrons from valence shell are not involved in bonding, it's only right to find out how many valence electrons are there. So just look at their groups. Oxygen is in group 6, so 6 here, 6 here, 6 here, 6 here. Sulfur is also in group 6, so 6 here. And hydrogen just has 1, so 1 here. So the total comes out to be 32 electrons, which are valence. So if 16 are shared, obviously 32 minus 16, that is 16 electrons not shared. Okay. So sometimes they do give you questions in which they will ask you to count them. And this is the way to count. You simply look at the lines to show how many electrons are being shared, and you can simply use the periodic table to find out how many are not shared. All right. All right. Sometimes we can find molecules that are unlikely. For example, AlCl3 is a molecule that is formed by metal. Aluminium is a metal, but it also forms covalent bond. So this is an exception to this. Now, what will we do in that case if we find something that has covalent bond and we don't expect it to do? We only look at the properties. Okay. So to look at the properties for anything, we will find the answers. All right. So first of all, let's try to understand how covalent particles behave. Covalent bonding is present in molecules. So, but each of these molecules is independent of the other one. Okay. What that means is that this molecule does not really need to bond to be close to the other electron, the other molecule. Okay. So if you have one water molecule, for example, then that water molecule does not really need the other water molecule because it is independent and it has completely filled all of its requirements. But they still have some weak forces of these IMFA are basically quite weak. They're weak compared to this. This is a covalent bond. Covalent bond is really, really strong. It's very hard to break. If you want to break it, you'll have to use chemical means. But IMFA are weak and they are broken using physical means. Okay, so that means physical properties, they depend on intermolecular forces of attraction. Okay, that's very important. So what are physical properties? Physical properties include melting point, boiling point, volatility, which means how easy does it evaporate, viscosity, which simply means how dense it is as a liquid. Okay, uh, these things depend on the molecules and their forces with each other. If the forces of attraction between them are quite strong, you will need to supply a lot of energy to break them. which means that the melting point will be high. We talked about this in the case of ionic substances, that the forces of attraction, electrostatic forces in that case, they were really strong, so you needed high energy to break them, which meant that ionic compounds, they had high melting point, high boiling point, high volatility, low volatility because they didn't evaporate easily, and that was because they had strong forces keeping them together. In the case of these molecular substances, there are no strong forces keeping them together. Why? Because what's happening is that these molecules, while they have strong forces inside them, like the covalent bond inside is really, really strong. But the force of attraction between one molecule, which is this thing, and the other molecule is very weak. So if you break that, you are easily able to evaporate that thing, you're easily able to boil that thing, and it will not flow as a dense liquid. So water is a very good example for this. It evaporates at any temperature before below boiling point. Why? Because it has weak forces which can easily be broken down. In fact, water is still has somewhat strong force of attraction compared to other gases like oxygen. So oxygen molecules have really, really weak forces. Okay, so these are also weak forces of attraction. And that is why oxygen is a gas. It boils at minus 196 degrees Celsius. That temperature, it seems that that temperature is good enough for oxygen to boil, for these forces to be completely broken down, minus 196 degrees Celsius. So that's how weak these forces are, and that even in those temperatures, they're easily overcome by the molecules. So remember one thing, that physical properties depend on these forces of attraction. Now, in molecules, we have them, but covalent substances also occur in other forms. For example, there is a substance that forms giant covalent lattice. These giant lattices are basically opposite of molecules. They still have covalent bonding with each other, but what's different is that every carbon, I'll take the example of carbon. So diamond and graphite are two examples of carbon where they have giant lattice. Giant lattice is basically any lattice. So ionic compounds, giant lattice. Uh, metallic substances, giant lattice. It's just that the lattice is of different things. In case of covalent substances, it is of atoms. In the case of ionic compounds, it's the formed by ions, so it's an ionic lattice. In the case of metals, it is also formed by cations, so it is ionic lattice again. In the case of covalent substances, it is atomic lattice. What's so special about atomic lattice? Atomic lattice is basically one carbon atom joined with another one, joined with another one, which are in turn then further joined with other carbons. And the process keeps on going, and this is basically one huge molecule that they've made. Similarly, in the case of graphite, that is one carbon joined with three carbons, which are then further joined with other three carbons, which are then joined with other three carbons, and the process keeps on going. And these are forming these layers, and these are forming this tetrahedral structure. Tetra means four sides of the structure. How come there are four sides? Let's look at this over here. So there are four carbons with the central atom, this central atom. So if I join them, I am able to make this pyramid that has four sides to it. Okay. So you can see that these are four sides. That is why it's called tetrahedral. And these are layers, which is why these are called layers of graphite. Now, here's the thing. These things behave very differently from these things. Why? Because they have different forces of attraction. And that is why their physical properties are different. So physical properties for these, first of all, their melting point, boiling point, volatility, viscosity, conduction, all of that depends on these physical properties. So it's really simple. There are two questions that you have to ask whenever you are given a compound or a substance. How strong are the forces of attraction in it? And does it have any free charge particles? That is the key to knowing its physical properties. So in the case of diamond and graphite, the forces of attraction are really strong. What does that mean? It means that you will need to supply a lot of energy to break them up. That means melting point is high, boiling point is high, volatility is low, viscosity is high if you melt them because they have strong forces keeping them together. In terms of conduction, do they have any free charged particles? Diamond does not. Silicon dioxide, which also has tetrahedral structure, that also does not. So that means that uh, they will not have anything to do with conduction of electricity. भाई इलेक्ट्रॉन है ही नहीं तो कंडक्ट कहाँ से करना है? But graphite, they have free electrons. Every carbon atom, it has 4 electrons, but यहाँ पर तो सिर्फ 3 नजर आ रहे हैं. तो वो चौथा का है, वो चौथा फ्री होके घूम रहा है, तो आवारा हुआ है. It is free to move around any way it wants. And that means that you can use that to conduct electricity because it is free. You give it energy, it will take it somewhere else. So graphite has 1 electron that is free for every atom. So imagine if you have a billion atoms, you have a billion free electrons. It is a really, really good conductor because of it. But diamond has absolutely no free electrons, so does not conduct. Let's talk about these molecules. They also don't have any free electrons. जो थे वो बॉन्डिंग में शेयर कर दिए, जो नहीं है वो पास पड़े हुए. फ्री तो कोई भी नहीं है. दैट मीन्स कोवेलेंट सब्सटेंसेस डू नॉट कंडक्ट. अब यहाँ पे एक सवाल है, why does water conduct them? And the answer is quite surprising. Water, when it is pure, does not conduct electricity. It is only when we have impure water that electricity is conducted. Similarly, all the acids, they are covalent substances. So they do not conduct electricity. But only when you put them in water that they start forming ions that conduct electricity. So you see, you just need any charged particle. And the uh, boundaries between covalent and ionic are not that uh, black and white. They are they're not that rigid because you see, we have seen molecules forming ions. We have seen molecules breaking down and making ions. So that is possible. But what is important for us to remember is how can we predict the physical properties of anything? So physical properties depend on two factors. How are the forces of attraction in there? And does it have free charge particles? In the case of molecules, we have weak intermolecular forces of attraction, which means they are weak, they're easily overcome, melting point is low, boiling point is low, volatility is high, viscosity is low, and they don't have any free electrons, no conduction. In the case of giant lattices, we know that diamond has no free electrons, no conduction. Diamond has strong force of attraction. So melting point is high, volatility is low, viscosity is high. Why? Because you need to supply a lot of energy to that for that to break. Graphite is an exception to this because graphite has free electrons. Now, it's not really an exception. It's just that it has free electrons, which make it capable of conducting electricity. So just three main types of substances here, and you just need to know two reasons you need for physical properties. Intermolecular force of attraction for that case, and simple force of attraction for that case, the giant lattices. And just know, does it have free charged particles or not, whether they are electrons or ions. Your question that anything with extra electrons can conduct electricity, we'll just say in one word there. Anything with free electrons will conduct electricity. As long as these electrons are free to move around, they will be able to conduct electricity. Do you mean what makes electrons free? So in the outermost shell, if they are not required. For example, in the case of metals, they have 2 electrons or 3 electrons that they don't want there. They want to get to zero. So they'll simply lose those electrons. So that makes them free. Similarly, in the case of graphite, there is the layers are very rigid. They are strongly bonded inside the layers, but the fourth electron, it is being attracted all over the place. So the forces cancel out and it's free to move around. So that's what makes electron free. All right. Thank you so much. Take care. Bye bye.